So from what we see here, a magnetic field is something that produces a force on moving charges, whether they're individual charges moving at given velocities or collection of charges moving at a certain rate through some distance, delta L, okay? And I could say more if you have a, this gives rise to a line integral. Okay, you just break a curved path into short segments and do this for every segment and take the limit as the length of segments approaches zero, right? And you get a line integral. So we're not going to ask you to do that line integral, but understand there is a line integral, okay? And there are plenty of implications of this. Okay, the other side of this coin is that moving charges create magnetic fields. So, moving charges. And what do we mean by moving charges? This would be charges that invoke an emotional response. Well, no. Okay. You know, had to bring your attention back there, I'm sorry. Okay, moving charges. Now I'm going to get all emotional about these things.
Oh, man.
It's tough. Okay. If you're not moved by this, then you're just not human. Okay.
Not charged enough.
Okay, moving charges. Experience forces in magnetic fields. That's what we're saying right here, and these are your basic rules. Everything else extends from these rules. Okay? Magnetic fields are created by moving charges. So you've got this kind of duality here or something. And I'm sure I could come up with better words if I was totally conscious right now. Okay, so, does that make sense? Yeah. Okay, what's the rule? The rule is the contribution to the magnetic field at a point, and this is much like, analogous at least, to Coulomb's law. Okay? First of all, you have a constant, K prime. Okay? And that's constant that you know, it's one of the easiest constants to remember. It's 10 to the negative 7th, and it's got units that when multiplied by these quantities give you Tesla, which is the unit of magnetic field, right? Right. So we'll figure that out after the law is stated here, okay? It's K prime, and then what creates the magnetic field? Well, it'd be a moving charge, right? But I'm going to do it in terms of a current segment, because that's usually what we think of. So the current segment is I delta L. The current I in some short segment delta L that's essentially straight, okay? And if you have a curved loop or whatever it is, well, again, you chop it up until every little piece is sufficiently straight, okay? And then it's over R squared, and then it's crossed with unit vector R over R. Now you can see the analogy with Coulomb's law, or at least with the definition of electric field, which eliminates one of the two charges, KQ over R squared, times the unit vector, right? But here it's crossed with the unit vector. Um, And R is a vector from the current segment to the point at which the field is calculated. So that's it. But to kind of understand how this works, we really need to work it out for a couple of configurations. Typical configurations being a long straight line of charge and a circular loop of charge, okay? So we're actually going to work that one out.